Well, hello everyone. My name is Antoine Ethève. I'm a bachelor student at the University of Geneva, and I worked on a summer project under the supervision of Professor Lombriser. The project was about cosmic reionization, which is the era that comes after the Dark Age. The Dark Age is the period during which the universe was neutral and no structure were formed. So reionization begins with the appearance of the first stars and galaxies. We don't know exactly when it began or what was the source of the ionizing photons, but we know that it ended approximately 1 billion years after the Big Bang. So the goal of this project is to develop a procedure to compute the reionization history throughout the multiverse from a given star formation with density. So to make sure that the procedure is correct, we will try to reproduce the results of Robertson and his colleagues that they published in a paper in 2015. And we will apply the procedure to a star formation rate density that was calculated from a model of star formation in the multiverse. Okay, so the first step is to calculate the redshift because all time-dependent quantities will be expressed in terms of redshift. Then we will be able to determine the star formation rate density the same way as Robertson, so we reproduce his results. And from here, we will compute the ionized fraction of hydrogen in the intergalactic medium. So this will give us information on the reionization history. And finally, we will discuss the coincidence problem of the reionization epoch. Okay, so the first step is to calculate the scale factor. It is given by the second Freeman equation. So we have 5 parameters that are evaluated today. So the first is the Hubble parameter. And then we have the 4 density parameters. So we have radiation, matter, spatial curvature, and dark energy. We want to ensure that the CMB temperature is 2.7 kelvins today. So we define the radiation density parameter from the energy densities of photons and neutrinos. Robertson gives the radiation energy density. And then we have to divide by the critical density given by this expression, where G is Newton's gravitational constant. So the ratio gives the radiation density parameter. For matter and spatial curvature, we just put in the values, the current values. And since the sum of all density parameters is equal to 1, we determine the last one from the others. We can now solve the equation numerically using a Python code. And then we use the relation between the redshift and scale factor to determine the redshift. Now that we have the redshift, we can compute the star formation rate density. So this is the formula that Robertson used in his paper. So it's a 4 parameters fitting function that we have to fit to observations. We will use 2 sets of observations, one from the Wilkinson microwave anisotropy probe, and one from the Planck collaboration that we will refer to as the maximum likelihood model. So Robertson provides in his paper the values of the parameter. So we just have to plug them in this expression. And then we have the star formation rate density that is computed from a model of star formation in the multiverse. So this one was computed by my supervisor, and he sent me a file containing the density. To make sure that we have the correct expression for this density, we compare a plot of the density against redshift to what Robertson published in his paper here on the left side. So on the right-hand side is our reproduction. The curves we want to reproduce are the white and orange curves, and they correspond to the red and orange curves on the right-hand side. So if we look carefully, we will see that the curves are identical. So we were able to reproduce correctly the results of Robertson. And we have one additional curve, which corresponds to the prediction of the star formation model. So it's not a perfect fit to the observations, but it is still in good agreement with them. The next step is to calculate the ionized fraction of hydrogen in the intergalactic medium. So the fraction Q is given by this equation, where we have n.ion is the cosmic ionization rate, so how many hydrogen atoms are ionized per unit of time and volume. So it is given by this product, where we have the star formation rate density multiplied by the number of ionizing photons that are emitted by a typical stellar population, and multiplied by the fraction of photons that escape to the IGM. The next quantity is the co-moving hydrogen density. So it is given by the product of hydrogen mass fraction by the boson density parameter and the critical density, all divided by the proton mass, so we have a number density. And finally, we have the recombination time, which is the time that it takes to an ionized hydrogen atom to become neutral again. So it is given by this expression, where we have C the clamping factor. We have the case P recombination coefficient, given by this equation. We evaluated at a temperature of 20,000 kelvins. And the last parameter to define is the helium mass fraction. So with these definitions, we can solve the equation for Q. And we use the initial condition that the universe is neutral before reionization, so Q is equal to 0. And then to compare with Robertson, we plot the neutral fraction, so 1 minus Q. On the left-hand side, we have the figure from Robertson's paper, and on the right-hand side, the reproduction. So I added some data points as well as the points from the white curve that we want to reproduce, here in green dots. So now it's clear that the white curve is exactly the white curve, and the both orange curves are identical. Now we can compare the prediction from the model of star formation in our multiverse to the observations in our universe. We can see that the prediction is not an exact fit to the observations, but it is still a good approximation. And finally, the last step of the project was to compute the evolution of the energy densities to check the coincidence program. So to do this, we solve the first Riemann equation. And we have to use the perfect fluid state equation that relates the pressure to the energy density. We have the factor W that depends on the nature of the fluid. For baryons, W is equal to 0. And we can solve analytically the equation to get that baryon density is equal to its value today times 1 plus z to the power of 3. For photons, W is equal to 1/3, and we have a similar expression. So the density is equal to its value today times 1 plus z to the power of 4. And the last density we're interested in is the dark energy density, which is constant and equal to its value today. So we wanted to reproduce the plots of cosmological coincidences that was published by my supervisor in one of his papers. And here it is on the left, and on the right-hand side we have a reproduction. So we can see from this plot that every time that two energy densities are equal, there's an apparently unrelated element that happens at the same time. The one we're interested in is the coincidence at the reionization epoch. So we have an equality between the photons and dark energy densities that happens almost at the same time as the instantaneous reionization, which is the time when half the universe is ionized. So it's not clear today whether these two events are related or not. To sum up, we developed a procedure to compute the reionization history from a given star formation rate density. We applied it to our universe and we produced the results from Robertson. And we see that we saw that our procedure was correct. We produced the observations from our universe. And we compared these observations to a prediction from a model of star formation in the multiverse. And we saw that they were in good agreement. So now the next step would be to compute reionization throughout the multiverse. And we can reproduce the coincidence plots in other universes to see whether this coincidence happen in other universes as well or not. If it always happens, then it probably means that the two events are related and there is something deeper to understand. Finally, I would like to thank my supervisor for giving me the opportunity to work on this project. I really enjoyed it. And I have now finished my presentation, so thank you for your attention.
on the conclusion slide, the second and the third point, I didn't fully understand the plot that you showed on the previous slide that showed the coincidence of reionization, star formation peak, etc., with the different equality redshifts. To what extent has this now been done throughout the multiverse rather than our universe?
It hasn't been done yet, but it's the next step of the project.
Okay.
Just I would like to add a point that so the question can be like, if we want to expand the code to a greater multiverse, so how will the code change according to the redshift, right? So when we are looking into the multiverse question, so we are looking at a higher redshift also, if I'm not wrong.
Yes.
Right. So how you will change this redshift? I mean, to accommodate larger redshift. So do you think that you need to change your code, or this code can only do the problem solving for the higher redshift part?
It can only do for the higher redshift part, because we were given a star formation identity, and from this we reproduce this plot essentially, and also this one. But in our code, we're not able to calculate the star formation identity.